Hello everyone, and welcome to the lesson on Loci. For you to be able to work out most of the questions on Loci, you require the prior knowledge on geometrical constructions. That is why on the screen you can see we are beginning off with a recap of what we have already done in the previous chapters, that is geometrical constructions. So for the patches on my screen, this is just a book that I scanned. That is why you can see the red patches. Now the instructions are very easy and they are not new. They are instructions that we all know. When you are working out on constructions, you require a pencil unless otherwise stated. Use a pencil, ruler, pair of compasses for all the constructions. Always follow the instructions that are given. Begin by drawing a rough sketch in most of the questions on construction before you go to the actual drawing or construction. The pencil should not be too soft or dark. Make sure that it is a sharp HB pencil. It is recommended you use that. Then the construction lines and arcs should be drawn clearly and must be shown. Do not disfigure your construction by repeated rubbing off. That is very important. Then some basic constructions are summarized below. So we're going to look at these basic constructions that you require, as I've said, for you to work out questions on Loci. Actually, most of them you require some prior knowledge that we did in the previous chapter. Number one, that is part A. You need to know how to bisect any line. Like in this case, you look at, you're bisecting this line PQ. Just go to the content that you did previously. How do you bisect a line? These just some pictures that I'm going through, but I'll not go through all these, how to bisect a line, how to bisect an angle. This is just to show you what you require to do before you come to the topic on Loci. So bisecting a line, that is how you bisect a line. You know how to mark those arcs. Then another thing that you need to know is how to bisect an angle. That is part B. How do you bisect an angle? Look at that also. Then another thing that I want you to look at is how do you drop a perpendicular from a given point. That is also very important. Then another one that is very important, and we use this one in constructing most of the angles, is construction of 60 degrees, an angle of 60 degrees, because it is from this angle that we get 30, we get 15, 75, and so many others. So that one is also very important. Now, after looking at those, we also have some other things that you need to know. Let me look at them here. So before we go to locals, let me see whether we have something else that we need to know. I think those are the most important things that we require to know for now. Now, let us begin off by going directly to the common types of loci. And we're going to begin by definition of this term, the locus. The plural of this word is loci. And this one means the locus of a point is a path traced out by a point as it moves according to some given conditions or rules. That is the definition. The locus, plural loci of a point, is a path. It is a path traced by a point as it moves according to the given conditions or rule. In a plane, the locus can be just one point, so it can be a point, it can be a line, or it can be a curve or a region of the plane. So that is the definition of the term loci. So it is a path traced out by a point as it moves according to some given conditions. We shall look at these conditions. Now the other thing which is very important is that to find the locus of a point P, you need to mark several possible positions of P which satisfy the given conditions until the overall shape of the path of P becomes clear. Now to understand that one better, we are going to start off by looking at this example that is here, example number 1. And this one is a question: what is the path traced out by a tip of the second's hand of a watch in the course of each minute? So this one is a very good example to help you understand what we mean by the locus. So we're going to use this is just a tip of the second's hand of a watch. Now the tip of the second hand, take up, let me draw these. So the tip of the second hand take up a number of separate positions P, that is P1, P2, during the course of a minute. These positions taken all together result in circumference of a circle, which is the locus of the tip. So as you can see, this path that is traced, so this second hand is started from P, then it moves to P1, it moves to P2, it moves to P3, to P4, to P5, and so on. So in the course of this movement, it traces a path, and that path is what we refer to as the locus of a point. So these positions taken all together result in the circumference of a circle, because it will form a circle, which is the locus of the tip. So the locus of this tip will be the whole of this circumference. That is how it moves, it creates a path. So there are so many other examples that you can use to understand locus. For instance, when you're opening the door, it traces a certain path as it opens, a certain angle, and that path is the locus of a certain point at a given distance. So there's so many other examples that you can use. I hope that one is clear. So we can go to something else, and this one is the first type of loci, the first type of loci, which is the perpendicular bisector loci. Now, which type of loci is this? This one is the locus of a point which moves in such a way that it is equidistant, or the same distance, from two fixed points A and B. I repeat this: the locus of a point which moves in such a way that it is equidistant, meaning the same distance from two fixed points A and B. This one is the perpendicular bisector of the line AB. So in simple terms, you can say that the locus of a point that is equidistant from two fixed points, that is two fixed points, in this case are A and B, that locus that is equidistant from those two fixed points is the perpendicular distance, or the perpendicular line which bisects the line that is given between A and B. So if you're given any two fixed points and you're supposed to get the locus of a point equidistant from those 2 points, you just need to join those two fixed points using a straight line. Then you construct the perpendicular bisector of that line. That will give that type of a locus. So in this diagram, as you can see, we have the line, that is the two fixed points are A and B, and so to construct the locus of a point equidistant from these two points, you just need to construct the perpendicular bisector of line AB. And in this case, you can see AP1 is equals to BP1, so it means they are equal. Then AP2 is equals to BP2. So for any point P on the line P1 P2, AP is equals to BP. So the locus therefore is this perpendicular line. Any point that lies on this line that bisects line AB, that is the locus that we are talking about. So that is the first locus. The second type of locus is the locus of a point. The locus of a point at a given distance. The locus of a point at a given distance. And we start with the first one, part A, the locus of a point at a given distance from a point. The locus of a point at a given distance from a point. Now, the locus of a point that moves in such a way that it is always at a fixed distance R from a fixed point A is a circle, center A, and the fixed distance, that is the radius, that is R, is the radius of the circle. So the fixed point is A, so the locus of a point that is at a fixed distance, that distance that is given here, that is the radius, and it moves such a way that it is always at a fixed distance from a fixed point. That one, you realize it is a circle, it forms a circle. That is what we call the locus of a point at a given distance from a given point. That point will move in such a way that it forms the circle. So all the points that lie on the circumference will satisfy that condition. We go to the next type of locus, that is part B, the locus of a point at a given distance from a fixed line. The locus of a point at a given distance from a fixed line. Now the locus of a point which moves in such a way that it is at a fixed distance from a fixed line AB is a pair of parallel lines at a distance D on either side of AB. So in this case we have a line AB, and then you're required to give the locus of a point which moves in such a way that it is always at a fixed distance from that line. So this is how we're going to get that. So these locus will be a pair of parallel lines on either side of AB. That is what will represent the locus of a point which moves in such a way that it is at a fixed distance D from a fixed line. So let's say this distance can be 2 centimeters. So you need to have 2 centimeters above that line and 2 centimeters below that line. That is the fixed distance D. So after drawing that, you notice that this one is a pair of parallel lines that is at the same distance above and below of that fixed line. So this is the locus and this one is the locus. So the other one is the angle bisector locus. The other type of locus is the angle bisector locus, the angle bisector loci. Now, which type of a loci is this? This one is a locus of a point equidistant from two lines, OA and OB. These are the most important things. The angle bisector loci is the locus of a point equidistant from two lines, that is OA and OB, the angle. And to get the locus which is equidistant from two lines, we get the bisector of the angle between the two lines. So in this case, since we need to get the locus of a point equidistant from two lines, OA and OB, we just need to identify the angle that is between these two lines, line OA and OB. So the angle that is between there, you bisect it. So when you bisect that, that will give the locus. So we also have another one here. This one is still the same thing. So we have OA and OB. So the locus of a point equidistant from these two lines is the angle bisector between the angle bisector that is between the two sides. So that is the angle bisector locus. Then from there we can move to the other type of locus. Before we do that, there's something here that is very important, that for any point, say Q on OP, the distances of Q from the two lines OA and OB are equal. So those distances, as you can see, if you just put any point here, any point Q, you notice that these distances are equal. So that is also a very important point. So the important thing is the locus of a point equidistant from two intersecting lines, AOB and COD, is a pair of bisectors of the angles between the lines AOB and COD. So this one is just talking about the same thing. The main point here is the locus of a point equidistant from two given sides is the bisector of the angle between the two sides that you're given. As simple as that. That is the most important thing that you're supposed to understand. Now we can go to the other type of loci is the constant angle loci. And the constant angle loci is very important. This one is very important. We need to pay attention to these. Now we have two parts here. Part 1, the locus of a point P is such that angle PAB is equals to theta degrees, where A and B are fixed points. So if you're required to give the locus of a point P such that PAB is equals to theta degrees, and you're given AB, in this case you can see you have AB, so you're supposed to construct the locus of a point P such that angle PAB is equals to theta degrees. Now when you construct these, theta can be any angle, it can be 60, 30 and so on. So this one will be a pair, angle PAB would be a pair of rays which subtends an angle of theta with AB on either sides of AB. On either sides you can see you have that side the top of that line and also below. So if let's say this angle theta was 60, you could just construct 60 there and 60 here. So when you take this angle, you notice PAB will give the same angle 60, and also down that line you have PAB is equal, so the locus of that point is a pair of rays which subtend an angle of theta with AB on either side. You can see that locus on that side and this side. So that is the first part that represents the constant angle loci. Now the second one, which is very important, is this one. The locus of a point P is such that angle APB is equals to theta degrees, where AB is equals to d centimeters. So the locus of a point P such that angle APB is equals to theta degrees, where AB is equals to d centimeters. Now for you to solve these, you require some prior knowledge on the properties that we learned in circles, chords and tangents. That is a property relating to the angle subtended at the center and the angle subtended at the circumference by a chord. So that is a property that you're going to use here. The angle subtended at the center of the circle by a chord and the angle subtended of the circumference by the same chord. And the property is simple. The angle subtended at the circumference by a chord, the angle subtended by a chord at the center of the circle is twice the angle subtended at the circumference by the same chord. That is a property. The angle subtended at the center of the circle by a chord is twice the angle subtended at the circumference of the circle by the same chord. So that is, you can see this angle here. The chord that is subtending this angle at the center is chord AB. This is the chord AB. So the angle at the center here is 2 theta, and you can see it subtends, the same chord subtends angle APB at the circumference. So if this angle is 120 at the center, this one 60. So that is the property that you're supposed to know here. So angle APB is equals to theta. Then for any point X on the circumference of the circle, angle AXB is equals to theta. Angles in the same segment are equal. That is another property you need to know. If C1 is the center of the circle, then angle C1AB is equals to 180 minus 2 theta divided by 2. So this is the property that I was just talking about, that the angle subtended by a chord at the center of the circle is twice the one subtended by the same chord at the circumference of the circle. So also this one is theta. You can even add another one here, even if you make another one, as long as it is subtended by that chord, that one will be theta degrees. So this is how you construct that angle. So to get this angle, let's say this angle is 60 here, and you're required to get, though you're going to solve this one, use an example. You're going to use an example for this to understand this one better, the example. So you need to get angle APB as theta and AB is d centimeters. So what you need to know, if you already know this angle, the circumference will be, let's say 60. If this angle is maybe this one was 60 degrees, you automatically know that the angle at the center here will be 120, and that angle is 120. This angle here should be, this one should be 30 and this one should be 30 degrees, because the sum of angles in a triangle is 180 degrees. So knowing this angle, you'll be able to know the angle that you require at the center here to be twice that angle, and that will help you to get the other angle here. So when immediately you construct 30 here and 30 here, where the two lines will intersect, they intersect at the center of the circle, you're going to use that center to construct these arc here. So knowing the angle at the circumference, subtended at the circumference, you'll know that the angle at the center will be twice that angle. And I'm giving an example. If for instance you know this angle is 60, you automatically know that the angle that you require at the center will be 120 degrees. So if you know that is 120, you just need to add another angle here. You get this one as 30, since this one will be an isosceles triangle. When you construct 30 here and 30 here, where the two lines meet, that will be the center of the circle. Using this center, you're going to construct a circle or an arc. Let me call this one an arc. So P will lie anywhere along that arc. So P will lie anywhere along that arc. Then that will not be the only side that you will give that angle. That P can be on either sides. It can be on the top of that line and on the bottom of that line. So the same thing you've done on the upper side of that line, you need to replicate that to the bottom side of that line. So whatever you've done this on the top line, you just do on the part. So you just come and construct here. Since you know this one is theta and this one is 2 theta and this one is theta, you'll be able to get this angle. By constructing this angle, you obtain the center of the circle. When you obtain the center here, you use that center and draw an arc, and the arc there. So the locus, that kind of a locus will therefore be any point that lies on this arc on the top of that line and also on the other side of the line. So the locus can either be on that side, the whole of that arc. That is what we refer to as the constant angle loci. So after doing that, I think we can try to solve this example that is here. Example on constant angle loci. A and B are fixed points 6 centimeters apart. Construct the locus of point P such that APB is equals to 60. So this is constant angle loci. So what you need to do, first thing, you're going to draw that line AB, which is 6 centimeters. Here it is, AB 6 centimeters. Let me bring it closer here. So you'll need to draw, you start by drawing this line AB, which is 6 centimeters. Then since you have angle APB is equals to 60 degrees, that is the angle at the circumference, you automatically know that the angle at the center, will be twice that. So you'll have 120 degrees at the center. So this angle is 60, sorry. If that angle is 60, then the angle at the center here will be 120. If this is 120 and this will be the center, therefore the remaining angles here, you are going to construct 30 here and 30 here. So the moment you construct 30 degrees on this side and 30 degrees on this side, the point of intersection of these lines will give the center. That will give the center, and already you know how to construct the angle of 60 degrees or 30 degrees using a ruler and a pair of compasses only. First construct 60 and then you bisect, you get 30. So constructing 30 here and 30 here, the point of intersection here will be the center of the circle. Then standing here with your pair of compasses, you just extend and get this radius, the radius AC1. Using radius AC1, that one will be the radius. You just draw an arc from A to B. That will be the locus of a point P. Any angle that you take here, any angle that you take, as long as it is subtended by, so this one will be 60 degrees, as long as that is subtended by this chord at the circumference, will be 60 degrees. Any that you take, can try to take another one there, so this angle is 60 degrees and so on. So that is how you locate the center. When you know the angle subtended at circumference, you just know the one at the center will be twice that angle, and that will help you to construct the center, to obtain the center. The same thing you've done on the top of that line, you do it on the bottom side of the line. So the center of this circle called C1, and then do the same on this side. Of course, you know this one will be 120, so this one automatically will be 30 degrees and this one will be 30 degrees. So meaning any angle take here, this one will be 60, so P can also be there. Any angle that you take here, because that is the angle subtended by chord AB at the center of the circle, this one will be 60 degrees, the angle at the center 120. So that is simply how you construct that. After working on those types of loci, we're going to this one that is remaining. We're going to tackle that one later. So the other type of the loci is the intersecting loci. To understand these, we're going to work it out using a question. The question reads, part A, construct triangle PQR, such that PQ is equals to 7 centimeters. Then OR, this one should be QR is equals to 5 centimeters, and angle PQR is equals to 30 centimeters. B, construct the locus L1 of point equidistance from P and Q to meet the locus L2 of point equidistance from Q and R at M. Then measure PM. So that is the question. So we're going to start by sketching this triangle PQR. So to sketch these, so you have P, you have Q, and then we can assume R should be, this is just a sketch, R is there. So PQ supposed to be 7 centimeters, then QR is 5 centimeters, then this angle here should be 30 degrees. That is a sketch. Now let's go to part B of the question. Now to construct these 30 degrees, you need to construct 60 degrees and then you bisect it. Once you bisect 60, you get 30. Then the other measurements, just need to measure them accurately. Part B, the locus L1 of point equidistance from P and Q. Now we need to identify which type of locus is this. Locus L1 of point equidistance from P and Q. You notice that that one is the locus of point equidistance from two fixed points, and that one we said that that is a perpendicular bisector locus of PQ. So to get that loci L1, we are going to bisect this line PQ. We construct perpendicular bisector of that line, and this is how we shall do it. So once we construct the perpendicular bisector, we shall have something like that. So that will be L1. Then the second type of locus is L2, the locus L2 of point equidistance from Q and R. Locus L2 of point equidistance from Q and R. That one also is the locus of point equidistance from two fixed points. So the two fixed points are Q and R. So to get the locus, we just construct perpendicular bisector of QR. So that one will be perpendicular bisector of QR. So QR is here. So when you construct that perpendicular bisector of QR, we shall get something like that. So this is just the sketch. So that is how we get L2. So where they meet, the two locus are meeting at this point, and that will be M. This is just a sketch. Then let's go to, because this one it hasn't been done, the answer is there. So you're supposed to do this one accurately, and I've done it here down here. It is here. So after constructing the triangle PQR, this is what I got. This one is I started by constructing 60 at Q. So this one is 30 and this one is 30. Then bisecting 60 to get 30. Then this one is 7 centimeters. This one is 5 centimeters. So after constructing the locus of point L1 equidistance from P and Q, this is the locus L1 perpendicular bisector. Then the locus L2 of point equidistance from Q and R, it is the perpendicular bisector of QR, that is L2. Where the two are meeting, this is the point where the two are meeting, M. So you just need to measure PM. The question measure to PM. Those are the intersecting locus. You can see the two locus L2 and L1 are meeting at this point. So measure PM, and by measurement you're supposed to get that one is 3.7. You can confirm these where that is the solution. So that is how we're supposed to work out that is intersecting loci. Let's go to the other type of locus, which is the loci of inequalities. The loci of inequalities. Now, an inequality is represented graphically by showing all the points that satisfy it. The intersection of two or more regions of inequalities give the intersection of their loci. Remember, we shade. Remember that we shade. Spelling mistake there. We shade the unwanted region. When you're representing inequalities on a graph, we shade the unwanted region. So let's do this one using an example. This is an example here. Draw the locus of point xy such that this is the first inequality, x plus y is less than 3. Then we have the other inequality here, y minus x is less or equal to 4, and then y is greater than 2. So you're supposed to draw the locus of point, let me stop this, the locus of point xy such that x plus y is less than 3. So there are 3 inequalities. So what you're supposed to do here, we are going to draw the graphs of each of these inequalities, and we've done this in the previous chapter. So if you've forgotten how to draw the graphs to represent the graphs of inequalities, just go back and do some bit of a recap of what you did. Now, so draw the graphs of x plus y is equals to 3. First of all, when you're drawing the graph, we just the normal way you draw the graph of a straight line, just get in 3 points, and then you plot the points. You just need at least 2 or 3 points to do that. So once you draw the graphs of these 3 lines, this is what you're going to get. You're going to get something like this. So the first one, y minus x is equals to 4, that is the line. Then y is equals to 2, that is the line. This one is the y-axis, and this one is the x-axis. So then the other one is x plus y is equals to 3. So those are the lines. We've said that we shade the unwanted sides, something that is very important here. The unwanted regions are usually shaded. That is very important to note. The unshaded regions, the unshaded region marked R is the locus of point xy that satisfy these 3 inequalities. And then don't forget this, that the lines greater or equal to and less or equal to are always solid or continuous, while the lines that are greater or less than, they are always broken. So when you're drawing those lines, less than or equal to, greater than or equal to, the lines are supposed to be solid or continuous. Then the ones that are greater or less, they're just supposed to be broken. Now, once you draw and shade the unwanted sides of each of those inequalities, there's that part that is going to remain, that is the unshaded, that is represented by R. This is represented by R. That is the required region, and that is the locus of point that satisfy the 3 inequalities. So that is the most important thing you're supposed to know, that the unwanted regions are usually shaded. The unshaded region marked R is the locus of point xy such that x plus y is less than 3, y minus x less than or equal to 4, and y is greater than 2. So that unshaded region marked by R is the region that satisfies all these 3 inequalities, and that is the locus of all those inequalities that are there. So that is how we work out the locus of inequalities. Now there's another one here. This one is just other types of locus that you can get, the types of loci that you can get the same on inequalities. I have another example. P is a point inside the rectangle ABCD such that AP is less than or equal to PB, and angle DAP is greater than or equal to angle BAP. Show the region on which P lies. Very important question. So AP is less than or equal to PB. What does that mean? So if you just get rid of this equal sign, you notice that AP, there's an equal sign there between less than or equal to. There's an equal sign. So AP is equals to PB. How do you do that? AP is equals to PB. Look at where A is and B is. So that means that you need to get P lies at the center of these 2 points, A and B. So to get that, to construct that locus, we just need to construct the perpendicular bisector of AB. And then, since AP should be less than, we don't need the side that is greater than, and that is why we have to shade this side that is here to the right hand side. AP is less than. Less than means that it should be to the left hand side. So the side that is on the right hand side, this side that I'm shading, that is the greater than, and that is the unwanted side. So that is how we do that. Then there's another one here. DAP is greater than or equal to BAP. So there is a greater than and there is equal. So if you just take DAP is equals to BAP, if you take that one first, DAP, look at where D is, A is, then P. We have already seen that the first P lies here somewhere there at the center there, then B, AP. That one tells you that this one is the angle bisector locus, so to satisfy this, DAP is equals to BAP, we just need to get the bisector of this angle, the bisector of DAB. If we bisect that angle, we shall get now DAP, this angle here, being equal to this, and that will satisfy this. So where should we shade? Look at this. DAP should be greater than. Greater than means that it should be on the upper side of that line, AP. So the side that is unwanted is the side that is down this line. That is the side that is less than, because we require the side that is greater than. The side that is above that line will be greater than, so we don't require that. So that is the unwanted. Remember that we always shade the unwanted sides. So you remain with the region, and that region that is unshaded, this is where P lies. Locus involving chords, and for this one, you're going to remind ourselves very fast about the properties of chords of a circle. So locus involving chords, the following properties of chords of a circle are used in construction of loci. 1. Perpendicular bisector of any chord passes through the center of the circle. That is a very important property, and we use these properties when we are solving some questions on loci. That the perpendicular bisector of any chord passes through the center of the circle. 2. The perpendicular drawn from the center of the circle bisects the chord. Perpendicular drawn from the center of the circle bisects the chord. Very important property. Then if a chord of a circle are equal, if chords of a circle are equal, they are equidistant from the center of the circle and vice versa. I repeat, if chords of a circle are equal, they are equidistant from the center of the circle and vice versa. Now, in this figure that is here, if chord AB intersects chord CD at O, AO at X is equals to X, BO is equals to Y, CO is equals to M, DO is equals to N, then M times N is equals to X times Y. This is the property of intersecting chords of a circle. That if these chords are intersecting, then you can say M times N should give X times Y. So this is a very important property, and we use it even when you're solving some of the questions that involve properties of chords. So that is all. Now we can be able to solve questions on loci easily, since we've gone through the definition of the locus and also the common types of loci.